Okay, in section 3 and 4, once again, I'm doing these two together because they're both looking at the populations and growth and things like that. So, um, to begin with, we're going to look at the difference between population density and population distribution. So population density is a measurement of the number of individuals living in a defined space. So if you've ever heard like how many people living in a square mile, that is an example of population density. So scientists can calculate population density by using the number of individuals divided by the area of units squared. That's going to be what the population density is. So if you hear like there's 100 people per square mile, that is an example of a population density. When we talk about distribution or dispersion of individuals, that's going to refer how the individuals are spread out in a given area. So there's a couple of ways that you can end up having a population spread out, and you see those listed along the side, but we'll look at some real examples of them here. So the first one is clumped. So clumped, they're going to be in groups like a school of fish, like you see in the picture there on the screen. Another example would be uniform. So it's going to be evenly distributed. So right here in this picture, you end up seeing birds that have built nests and they're evenly distributed. They basically, when they make nests like this, they have like their little pecking ring. If anything is too close to them, they're going to keep pecking that bird until it moves a little bit further away. And then you've got random, which in this case it's showing a sloth, or most animals it's going to be random that you're going to end up seeing. They're not going to be in clumps or schools or things like that. They're going to be out individually and spread out wherever they may be. So when we talk about population density and distribution, you have what are known as survivorship curves, and they're going to help describe the reproductive strategy of a species. So a survivorship curve is a diagram showing the number of surviving members over time from a measured set of births. So you can see in this chart right here, 0 to 5, you had 1 death, so 35 survivors. Minus 1 is going to give you 34, and that's going to give you a 97% survival rate. And you keep looking at that as you go, and you'd be able to figure out and actually graph that type of a thing out. And that's what you're going to see here. So survivorship curves can be type 1, 2, or 3. Type 1, you have low level of infant mortality and an older population. So this is going to be common to humans and mammals. Type 2, the survivorship rate is equal at all stages of life. That's going to be common to birds and reptiles. And then type 3, very high birth rate and very high infant mortality. So this is going to be common with invertebrates and plants. So here you can see in this graph over here, the orangish color is representing the, again, mammals and humans. You can see that it's going to be pretty high for the lifespan of the organisms. The green is the one that's the reptiles and bird. You can see that it's pretty much a straight line. And then you can see the one that has the high mortality the whole time, basically a high birth rate and high mortality rate is going to give you that type of a curve for a survivorship curve. Okay, in section 4, we're going to look at different growth patterns. So ways that you can change a population size, they're going to be, you can increase the size of a population by having individuals move in and having a higher birth rate than a death rate. So the size of the population most of the time is always changing. You can have what is called zero population growth, and that doesn't mean that you're not having individuals born or people moving in and no one dying. It means that it's equal. You're going to have equal number being born as are dying, or equal number coming in as going out of your population. So populations usually are always changing. So there are four factors that affect the size of a population. Immigration, which is people moving into an area. I think of immigration with the I is into. You have births, which you would have, if you have a lot of births and not many deaths, that's going to increase population, or not very many births, you're going to end up having, and a lot of deaths, you're going to have a negative population growth. Emigration with an E is individuals leaving an area. So that the E, I think of exit. And then deaths is going to be the fourth factor. And again, if you have high death rate, low birth rate, you're going to see a population that's declining. If you've got high birth rate, low death rate, you're going to see a population increasing in size. So when we look at a population, you are always going to end up seeing a period of what is known as exponential growth. And that's going to be rapid growth. The growth is going to increase due to usually an abundance of resources. So it's going to be things like enough food, water, shelter, mates, things like that are going to allow for exponential growth to occur. And when we see an exponential growth curve, it's usually going to be a J-shaped curve like what you see here in that picture that just popped up. So that's exponential growth, and it says it will keep going like that indefinitely until you run out of those resources. So exponential growth only happens for a certain amount of time in real life. It will then switch to what's known as logistic growth. So logistic growth is the normal growth, and it is due to a population facing limited resources. So as we look at this graph right here, there are a couple of different parts of this graph. You have the period of exponential growth. So that's going to be from here over. That's going to be the J-shaped curve right there. That's exponential growth from about here to here. This is going to be so that's stage one. Here's stage two. Stage two is going to be the growth slows down. It's still growing fast, but it slows down. And then stage three is going to be the stage where the growth levels off, and you're going to end up having zero growth rate. You're going to end up having something has limited the population size, and you're going to have equal number of births as you do deaths. So those are the three parts of the logistic growth. When it gets to that part where it levels out, we have what we call carrying capacity. Carrying capacity is the maximum number of individuals that particular environment can support. So a population crash is a dramatic decline in the size of a population over a short period of time. You can have what's known as boom or bust, where you'll see I'll draw it out, you'll see a population that will go like rocketing it up like that, and then it can drop down pretty rapidly. So that would be part of a population crash. So that is what's known as boom or bust as well. So here's another example of it where you see in this the rainfall amount in inches. You'd end up seeing a rapid decrease in the. You can see the fish population is really high, and then you had not as much rain, rain starts to go down, and you end up seeing the population of fish end up going down as well. So things that are going to be what is known as the carrying capacity, we refer to those things as limiting factors. So a limiting factor is something that keeps the size of a population down. And there's two main types of limiting factors. You can have density-dependent limiting factors and density-independent limiting factors. So density-dependent limiting factors are affected by the number of individuals in a given area. They're going to work best on large, dense populations. So that is what a density-dependent limiting factor is going to be working on. And here are some examples of density-dependent limiting factors. So predation works best when you have a large population of prey. The predators are going to easily be able to pick off the prey. Competition, so competing over all of the available resources within a population. So like when we were outside for that oh deer game, you ended up seeing competition in that game and saw the populations going up and down of the deer. Parasitism and disease are going to be things that are also considered easier to happen when you have a large, dense population, because that parasite can easily jump from one individual to another. Disease can easily jump from one individual to another. If you have a large spread out population, you're not going to end up seeing a disease easily passed. So, and this is giving you an example of something that you'll sort of see in a lab that we're going to be doing for this section. So density independent limiting factors, just like the name sounds, is it doesn't matter the size of the population. It's going to work on that population regardless of how dense it is. It could be a really scattered population or a really dense population. It's going to work the same. It's equal opportunity one. So examples of this would be unusual weather, natural disasters, and human activities are going to be examples of things that would be considered the density independent limiting factors, and they're going to limit a population size, and again, they don't care what the size of the population was. So that's the end of the notes for section 3 and 4.